Hello, my name is Aaryan Chatterjee, and this is my Charge Tape Lab 1 in Physics 2212. Before getting directly into the lab, it's important to understand what the lab is precisely covering, which are charge-object interactions. In real life, objects in the world have a fundamental quality called charge, and objects can have a positive or negative charge. Now, in this lab, we will focus on analyzing the interactions of two pieces of charge tape. More specifically, the purpose of the lab is to analyze the interactions of two pieces of charge tape, predict the charge of the tape, and determine the excess or deficiency of electrons in the tape. We'll also use a computational model to represent the interactions of the charge tapes, and we'll compare our results to it. Later, we will see that our analysis in the computational model analysis will tell us that the charge of the tape is 1.12 times 10 to the negative 8 coulombs, and the electrons in excess were 7 times 10 to the 10. Additionally, the picture on the right will show us what the experiment we will do will look like. But before we jump straight into lab specifics, it's important to understand some of the crucial physics principles and ideas utilized in this lab. Firstly, it's important that everyone understands Newton's second law, which says that net force equals mass times acceleration, or change in momentum over change in time. Additionally, it's important to know that the force of gravity on an object on Earth is negative mass times acceleration, which is g, or 9.8. Finally, it's important to know that Coulomb's law, which describes the force between two charges, and this is the formula here on the slide. These forces will be needed in the observational and computational model to calculate everything, like the charge of the tape, number of excess electrons, and more. Now we must cover some major assumptions in the experiment, and one is that the object only experiences a gravitational and electrical force. This means that we will not consider any external forces that could have acted on the tapes. On top of the assumptions, it is important to know that the system, which is what we will analyze, is simply the top tape, which is tape B in the experiment, and everything else is surroundings, like the bottom tape and the ground. To get into some detail about the experiment, we will have two tapes aligned vertically, causing the top tape to float since the tapes repel each other, since they will have the same charge. Then the top tape will be at rest while floating in the air, and this is due to the electric force and the gravitational force acting on the tape. So for the actual experiment, we first tested how a charge tape would react to a human hand and a pen, and this video shows the interaction with the human hand. We can see that it tracks to the hand, and after doing more tests with the tape, it is clear that the tape is positively charged. Then we recorded some important information about the tape that we will need, and we learned that the tape mass is 2e negative 4, the tape length is 0.2 meters, the tape width is 0.02 meters, the atom area is 1e negative 10, and the total atoms on the tape is 4e plus 17. Then we set up the experiment where the tape floats, and we found that the distance between the tapes were 0.024 meters. Now, with all the information, we can calculate the charge of the tape, the number of excess electrons, and the ratio between the atoms and electrons in the tape. First, we can find the gravitational force on the tape by doing mass times acceleration, which gives us 1.96 times 10 to the negative 3. Then, since the tape was at rest while floating, the gravitational force must equal the electric force between the two tapes. So the electric force is 1.96 times 10 to the negative 3. Then we can solve for the charge in the electric force equation since we know everything else. And we found the charge to be 1.12 times 10 to the negative 8 coulombs. Then we can find the number of electrons on the tape by dividing the tape charge by the charge of an electron, which tells us there is 7 times 10 to the 10 electrons on the tape. Then we can find the ratio between the atoms and the electrons on the tape by doing the number of atoms on the tape divided by the number of electrons on the tape, which gives us 5.7 times 10 to the 6th. Moving on to the computational model, we first put in the known constants like the gravitational acceleration, tape distance, tape length, tape width, and much more. Then we calculate the gravitational force, then solve for the charge of the tape. Then the computational model solves for the number of electrons in the top tape and finds the ratio between the atoms and electrons. And as we can see from printed results, the computational model finds the same answers as us. Again, as I just said, the computational model and the observational model provided the same exact answers, as they both said the top tape has a charge of 1.12 times 10 to the negative 8, the number of electrons excess is 7 times 10 to the 10, and the ratio between the atoms and electrons is 5.7 times 10 to the 6. Thus, it can be seen that we calculated accurate results. Now, although the computation and observational model got the same results, our calculations could have been wrong, since if the distances of our tapes were measured incorrectly, almost all our calculations would be different. Additionally, the drag force and the other external forces were not considered, and they could have affected our tapes. Before I end this presentation, it is important to answer some key thoughts. For instance, if electrons and protons switch charges, it wouldn't affect the experiment at all, so the tapes would still have the same charge as each other regardless, meaning the tapes would continue to repel, allowing the experiment to occur and one of the tapes to float. Additionally, it's important to handle the tapes as little as possible because the tapes interact with other objects in our hands to try and become neutral charged again, and if that happens, our experiment wouldn't work, so we want to handle the tapes as little as possible. That's all from our presentation. Thank you for listening.